All right. So this is an example from your book. This is example 347. And in this example, it says we have an automobile front suspension, and it consists of two A-arms, the wheel with the tire, a coil spring, and a shock absorber, which is our damper. The effective stiffness of the suspension, which in the trade they call the ride rate, is a function of the coil spring stiffness and the tire stiffness. The A-arms are designed to give the wheel a nearly vertical displacement as the tire rides over the bumps. What that means is that we can just treat it as a mass spring damper in one direction. The entire assembly can be modeled as a mass spring damper if the sprung mass, which is the mass portion of the vehicle supported by the suspension system, is 675 pounds, which might be about a quarter of the total vehicle weight. Determine the ride rate, which is the stiffness for that spring, to achieve an undamped natural frequency of 1.4 hertz. So this is a little bit different way of asking the question. It's saying, what is the desired stiffness? So then we can design a spring to give us this natural frequency against this load. And then the second question is, what is the static deflection of the suspension? Okay, so we can go over here and take a look at this case. This is that's for a different example. It's for the next example. And we can start to analyze the system based upon what we were given in the problem. Okay, so this is problem in your book, which is 3-6. Okay, so this is okay. So this is problem 3-6. Okay, and we're told that, oh sorry, this is problem 3-47. Okay, and we're told that the weight of the sprung mass is 675 pounds, and that's pounds force, not pounds mass. Our desired natural frequency is 1.4 hertz. Okay. The sprung mass, we would like our units to be in inches. Okay, so we can take the sprung mass, which is going to be the weight over gravity. In this case, it's 675 pounds force divided by 32.2 feet per second squared. And if we want to get it in inches, we can divide it by 12, and that'll give us 1.748 pounds force per second squared per inch. And then the ride rate, which is the stiffness, is going to be omega squared, omega n squared times the mass. Okay, and that just comes from our equation here, where our natural frequency is the square root of k over m. Okay, so if we do that and we plug in the expressions for the natural frequency and for the mass, then we can get the weight then. And we got to be careful here because we have the units here in hertz, okay, but when we have omega, omega is in radians per second. Okay, so to convert to hertz, omega n is 2 pi f. Okay, so before we square that term, we need to multiply 2 pi times the 1.4, and then we take that quantity and we square it, and then we multiply it by the mass, 1.748 pounds force, and make sure this is in units of per second squared. We're multiplying it by second squared, so those will cancel out. And then, so what we should expect is that we'll get, when we solve for K, we'll get a force over stiffness. Okay, so if omega is n is that, therefore, if we multiply these terms, that's equal to K, and that's going to be in pounds force per inch. And so we can find then that K is equal to 135.28 pounds force per inch. And then the question is, what is the static deflection? So now that we have the stiffness, we can calculate our deflection. Our deflection is just going to be equal to the sprung weight over the stiffness, the force over the stiffness. In this case, the deflection then is going to be about 4.99 inches. So we get, for that ride rate and for that load, we'll get a deflection of about 4.99 inches. So this is just one way to do that. I'm sorry that it came off the screen here, so let me bring this up here for these last equations. So if we solve, if we plug in the omega n, we convert it from hertz to angular frequency, and then we multiply the frequency squared times the mass. That gives us our stiffness. Once we know our stiffness, we can take our load and divide it by that stiffness, and we get the deflection of 4.99. Okay, so that's one example of how we would do that. All right, and so this is example 3.6. This is to look at the impact loading. This is for the trailer hitch of example of problem 3.4, which is trailer hitch here. It says determine the horizontal force that will result on the ball from an impact. Okay, so on this ball, from an impact between the ball and the tongue of the 200 kilogram trailer if the hitch deflects 2.8 millimeters dynamically on impact. The tractor weighs 1,000 kilograms and the velocity at impact is 0.3 millimeters per second. Okay, so we're going to take a look at that. In this case, we have this drawing up here. This is problem 3-6. Okay, we are told that the mass of the trailer is equal to 2,000 kilograms. We're told that the tractor is, the mass of the tractor is 1,000 kilograms. The impact deflection is 2.8 millimeters, and the impact velocity is 0.3 meters per second. Okay, so the tractor is the struck member. Okay, and that's because the hitch is on the tractor and it's the hitch that deflects. Okay, and so we can use the equations from the book. These are equations 325 and 326 to get a relationship. First, we want to calculate the actual weights, though, so we can calculate the weight of the trailer. It's just the mass times the gravity here. Okay, and that comes out to 19.613 kilonewtons. We need to find our eta, our correction factor, okay, which is related to the ratios of the masses of the objects. And that comes from our expression here, where we have 1/1 plus the mass of the tractor. That's our struck mass, over the striking mass, which is the mass of the trailer. Okay, so if we put in our masses here for the trailer and for the tractor, and we solve this, we find that eta is equal to 0.857. And then we can use our equations for the impact, and those are these equations here, because we would like to find the horizontal force. So we need to introduce the force term. So we say 1/2 times the force of the impact times the deflection of the impact is equal to the energy due to the velocity, which is eta times 1/2 the mass of the trailer times the velocity squared. Okay, so in this case we're using the mass of the trailer because this is the striking mass. And then all we have to do then is solve for the forces. Okay, so we solve for the force, say that the force is just equal to eta mass of the trailer times VI squared over delta I, and we can see that that is 55.1 kilonewtons. Okay, so this gives us a way of calculating force. Now remember, this impact force is 55.1 kilonewtons, but the actual weight of the trailer was only 19 kilonewtons, and so because we have this impact event, we get a much higher forces. Okay, so this is just an example of how you would use these equations to analyze impact between a struck and striking mass, and using the energy equations.